Hello students, how are you all? It is nice to come back again to the physics lesson. Hope you saw yesterday's video, which is about the topic of collisions. So it was a video with only one derivation. We finally derived the final velocity of v1 when a body collides with another one. And then we saw the velocity v2 when it collides. So I hope you understood things very well. Like the first velocity was u1 of the body A of mass m1, and then the next body was a little small with a little velocity, not so big, and so that's the reason, because this is a bigger mass, it just came and it was able to hit this one at one point of time. So after hitting, then this is the velocity this A was having, and v2 is the velocity this B was having. So that's the way we finally found this one. We also saw the case of case 1, case 2 and things like that. I wanted to just emphasize on the cases that we saw so that it will not be just missed out. Yesterday I was feeling that I didn't explain the cases quite well. So if you look at the last part of the derivation, please take the register and see how you have derived. So if in case you get into the position of like this, two bodies in case 1, both the bodies are having same mass m and mass m, and this body is going with the higher velocity u1 and this is a smaller velocity u2. So obviously this is going to come and hit this one. You can take an example of carom coin. The carom coins are all of same masses. So you flick a carom board coin itself, not the striker. A coin is hitting another coin. This is the higher velocity, this is the lower velocity, okay? So as it hits, after collision, what happens here? So this will have a velocity v1, this will have a velocity v2. But when we look at the expression, in the expression what happens? Both the masses are same. So this will also m, this is also m. This will become value v1 is going to be equal to 0, because this m and m will get cancelled. It will become 0 plus. So what this will become? 2m u2 upon m plus m. That also will become 2m. So this 2m, 2m also will get cancelled out. So v1 is going to be equal to u2. So what is v1 is equal to u2 means? v1 is equal to u2 means, so this v1 will be the same velocity of the body A. This body A, this v1 will be equal to u2 here. Thus B will be giving the velocity to A. So when this A comes and hits this one gives the body velocity to this one. So that's what v1 is. Similarly, this A will give the velocity to this one. So v2 will become equal to u2 then. So that's the way it exchanges the velocity. Earlier vu1 was there, and this will go in u1 velocity, and this will go in that velocity there. So that's the way it is. If you look at this one also, v2 also will become the same way. It becomes cancelled out, and plus 2m, this will become 2m, and this is u1 here upon this also 2m. So 2m, this gets cancelled out. So v2 is going to be equal to u1. So the velocity gets exchanged. That's what I already said this one. Case 2. Case 2 was something you wrote about a very massive velocity mass. So we will come back to that. But case 2 is little different. We are just going to see another case 2 here, right? This case 2 is same masses only, mass m and m, when m1 is equal to m2 is equal to m. This is case 2. Maybe you can tell this case 3, because you have already written one case 2, it's okay. So we'll take it as case 3 here, right? Two masses are same, but u2 is at rest. This body is at rest, B is at rest, and this is only raising up and then hitting a stationary body here. What will happen now after collision? It just straight away comes and hits, and remember both the masses are same. So two bodies are there and u2 is going to be equal to 0. In that condition, so you will have the masses expression. Now the two masses expression will change, right? Already you got this way of things. Already you got V1 is going to be equal to 0 because when two masses are same, you will get the same expression here. Now at the same time, you get here U2 is already equal to 0 there, right? Because this value of U2 is going to be 0. So if this is already equal to 0, now V1 is going to be equal to 2m U2 upon 2m is the actual thing. It comes from here, 0 plus this one. That's the way it comes. This also gets cancelled. Now V1, it should have been equal to U2, but here U2 is already 0 here. So V1 will become also equal to 0. So that's the way it will become. And V2, what will V2 will become? That will not be disturbed because it is 0 plus 2m U1 because there are two masses are same. So we can take up the same expression here. So two masses are same because m and m, it will get cancelled. This is 2m. Again, this whole thing will become 0 because m and will get cancelled. 2m upon 2m, this 2m upon 2m, and this is u1, the same u1 is here. So in this way, this 2 also get cancelled out. So v2 is equal to u1, that will be the same. v2 is equal to u1 will be the same. But only thing is, v1 will become equal to 0. What does it convey to us? What is this whole thing is conveying to us? After collision, this body will take rest. This body will start moving. Now V2, the body B will be going in the same velocity of A. So V2 is going to be equal to U1. So it comes and collides, and this will start going in then velocity. This will start moving and this body will take rest. A body will be at rest. But B body will be going in a velocity as that of the A body here. So that's the way it is. So have you seen two carom coins coming and hitting? As soon as it hits, this body will come to rest and this body will start moving the same velocity of the previous one. So that's what it is. So you can write down the moving body, the first body comes to rest after collision. And the second body moves with same velocity of first body. Case 4. We'll see case 4. So what is case 4 is? So case 4 is, look at this expression here, look at this diagram here. A tiny mass m1 is coming and hitting a stationary mass m2 which is huge. This is m2. m2 is greater than m1. But look at this one. Interestingly, this body is at rest. m2 is not moving. u2 is equal to 0. It is at rest. So the small mass is coming and hitting. What will happen then? Actually what happens is, when the small mass is coming and hitting, this mass will start, after hitting it will start rebounding back. It hits and now it's going back. It goes back with a velocity here. And what happens to this big mass? It will again keep on stationary only. It will not move anywhere. It will be there only. V2 is also will become 0. U2 is 0. V2 will become same 0 only. It will not move. But this mass, it comes, hits and it ripples back. So that is the beauty of this one. When huge mass is at rest and another mass, tiny mass is coming and hitting. Now we need to give it in a part of an expression. We need to really tell it in a part of expression. We cannot just tell, yes, this is what will happen. So now let us get back to the actual expression itself and see how it works here. So in this one, you are going to neglect m1. So here you find when this is so big, m2 is big and m1 is small, so you can neglect m1. So neglecting m1. When you neglect m1, just drop this one. Wherever it is there, you just drop it. Okay. So you can write the expression once again. And also u2 is 0. neglecting m1, and u2 is going to be equal to 0. So u2 you have to put 0, this entire term will become 0. Right? So v1 is equal to, after the plus, this entire term is 0. u2 is 0, so I have put 0 here. And what is happening here? Wherever m1 is there, just drop it. So u1 minus m2 upon, here m1 is there, just drop it and then take only m2. It is m2 is there. This gets cancelled out. There's a minus sign already hanging here. v1 is equal to minus u1. That's what it happens. Right? v1 is equal to minus u1. Let us do it for the second expression also. This expression. So u2 is 0 because it is at rest. This body is at, B is at rest. So u2 is 0, this whole thing will become 0. So when I take v2 here, 0 plus, because it's u2 is 0, it becomes 0. And wherever m1 is there, you just drop it. So you get here 2u1 upon m2. So that becomes the expression here, where this body will become, this is the first v1 velocity and this is v2 velocity. But here you find m2 is so big, large. This is sitting at the denominator. Right? A huge body is sitting at the denominator. It's a very big number. In the top you have a very small number, which means v2 is approximately equal to 0 itself. v1 is going to be equal to minus of u1 and v2 is approximately equal to 0. So that's what the expression makes. Now what is that when it see in the diagram point of view? Look at the diagram point of view. I told you already, v1 will be equal to minus u1 because it rebounds back. It is a negative, it just goes and rebounds back, and v2 will finally, it will be at the same rest position itself because it is so huge, and with the very small quantity in the top, so it will be approximately equal to 0. So that's the expression, which is the case number 4. Now we'll go to case number 5 now. Case number 5 is the reverse of this one. What is the reverse of this one? A stationary body is a very tiny body. This u2 equal to 0. It is at rest, and this is m2. But the body which is moving, it is a huge body is moving and coming and hitting this one. What will happen? So after hitting, what happens is, after hitting, you would find the huge body continues to go in the same velocity. v1 will be equal to the same thing. v1 will be equal to u1 itself. Whereas the tiny body will start going in twice the velocity of u1. So you will be able to see in the expression how it will be there. So in this expression, what you will do is, since m2 is really small, so what you will write here, case 5, when m1 is greater than m2 and u2 is going to be equal to 0. Neglecting m2. So in the expression, you need to neglect m2. So where is the expression? We'll see the expression here. And you're going to neglect m2 here in both expression, and at the same time u2 is 0. So when u2 is 0, this whole thing will become 0. So v1 is going to be equal to, this whole thing has become 0 here. Only this one survives, and m2 you need to drop it. Just m2 you drop it. So it's going to be u1 into m1 upon, this is m1, the same m1 is here. So what will happen? v1 is going to be equal to u1 itself, because these two get cancelled out. So that's the first expression. v1 is going here. Now what happens to v2 here? v2 is going to be equal to u2 is 0. Since u2 is 0, this entire expression is 0. So you put 0 here, plus. So what happens here? What is supposed to be dropped? Neglecting m2. So you just drop m2. So it becomes 2 m1 u1 upon m1. Only m2 is dropped. Just you would leave it. Now these two gets cancelled out. So v2 is going to be equal to 2u1. Hope you are able to get the expression out of this. So just putting these values and we are getting two expressions. Now let us try to translate into the diagram part of it. Now look at the diagram part of it here. So V1 is going to be equal to U1. So V1, this V1 will become equal to the U1. That means this body is not going to change this velocity. It just keeps on massive body, it collides and still going the same velocity itself. Not even a single effect it has happened because of collision. V1 is going to be equal to U1. Now what the tiny body does? Tiny body goes in twice the velocity of U1. It is called 2U1, it's here. That's what it was already told, and that's the way it becomes also. So you have to write here, the massive body goes in the same velocity. Can you please write? The massive body goes in the same velocity. But the smaller body, which was at rest, after collision, moves in twice the velocity of the massive body. Hope you are able to understand this beautiful ways. So I just made a diagram so that everybody can easily understand. Two masses of same masses. Then after collision, it will exchange the velocity. B velocity will go to A and A velocity will go to B. Two bodies, one is at rest and next one is there. Then what happens? This body is moving, will come to rest. This body will start moving in the first body's velocity. Next one is a huge body is there at rest. This is coming and hitting. It will rebound and come back. The huge body continues to be at rest. A huge body is hitting a restful body. A huge body will continue to move the same velocity, but the rest body will start moving the twice the velocity of the first body. So that's the way it is. Quite a good illustration, but it is very important to understand all the cases. We'll move to the next one now. Going to page number 348. Yesterday itself we saw inelastic collision in one dimension. Remember, inelastic collision in one dimension is something, we saw it yesterday itself. What is inelastic collision? Where momentum is conserved. We saw momentum is conserved, and then we saw this one. Momentum is conserved, energy is conserved in inelastic collision, but kinetic energy is not conserved. What is the reason of kinetic energy is not being conserved? That means the initial kinetic energy of A and B put together. So B is here, A is here, V1, U1 here and U2 here. It has the total kinetic energy, and after collision the way A goes and the way B goes, remember, if you put the kinetic energy, this kinetic energy 2 and kinetic energy 1, this will be more and this will be less. Definitely lose the kinetic energy. So that is the way it is. So there is a not equal, it is not equal. This will be greater, this will be less in an inelastic collision. Now you can say where the kinetic energy is lost. It has got a huge kinetic energy, now it has got a less kinetic energy. Where it is lost? It would have lost in the time of sound energy, maybe when it collides, that's a sound. Maybe it creates some spark, so it could have gone into high light and heat energy, and it would have done some kind of a damage also to itself, so it is rubbing each other. So inelastic collision, it loses the energy in between. In regular life, in everyday situation, all the collisions will be inelastic only. A car and a motorcycle hits head on, or maybe a moving car is there and a truck coming from behind in a higher velocity comes and hits this one. These all the collisions are inelastic because sound energy comes, light energy goes, and so many things is there. So the total kinetic energy before collision and total kinetic energy after collision will not be same. Elastic collision happens in today's world also, it is there. It is a very, very idealistic condition. One in molecules it happens inside the chamber. Air molecules goes on an elastic collision. So that's the way we understand. But inelastic collision is pretty common in everyday situation. The derivation which is derived here is not important. You need not learn this derivation. I'm not going to derive this one. So please don't derive this one. It is not so important. But definitely there is going to be a loss of kinetic energy during inelastic collision. So it will be, some difference will be there. The last part of this theory portion is elastic collision in 2 dimension. This also I am not going to derive, but I will tell what it is. So here a body of M1 is coming and hitting. This body is M2. After hitting, we always assume everything is going in a straight line. That's what we say, no? It goes again the same straight line itself and going in one velocity and another velocity. But here, what if one goes like this and another goes another direction, like a carom board coin? You just hit, both of them don't go in the same line itself. The body is getting a hit and the body is going to hit. Both of them don't go in the same straight line. One goes here and one goes here. That is called elastic collision in 2 dimension. In 2-dimensionally it is going. So what happens? There's a theta 1, there's a theta 2. You need to take the components of the velocity of m cos theta 1, cos theta 2 and all this stuff and then go ahead. I'm not going to derive this. This is also not very important as far as the theory portion concerned. Maybe there are some numerical comes, we will be able to handle those things with certain other parameters. But need not learn this as a derivation. Right? Now if you look at the next page, with that the theory portion of the whole chapter gets over. There's a small part called coefficient of restitution is there. And coefficient of restitution means E is equal to 1. I think yesterday itself we saw about the relative velocity of approach and relative velocity of reproach. That is something to do with the velocity in which it will come and hit the body, and as well as the velocity in which the body will start moving in the next direction. So we saw velocity here, u1 minus u2 is equal to v2 minus v1. This is the one we derived. The relative velocity of initial velocity. Relative initial velocity is equal to relative final velocity. Now this one, the ratio is called E. So it is called relative velocity of approach is equal to relative velocity of reproach. So relative velocity of approach is equal to relative velocity of reproach. So u1 minus u2 upon, it is going to be equal to u1 minus u2 upon v1, v2 minus v1. That's called E. This is E is coefficient of restitution. The coefficient of restitution is here. The coefficient of restitution is defined as, what is the definition? It is a ratio of the relative velocity of approach to the ratio of relative velocity of reproach. That means this velocity upon this velocity is E. Now when will be E will become equal to 1? E will become equal to 1 for an elastic collision. So for an elastic collision, E is going to be equal to 1. Look at this 1. For a perfectly elastic collision, E is going to be equal to 1. For a perfectly inelastic collision, E is equal to 0 are taken. So this is the way in which E is 1 and E is equal to 0. What is E? It is called coefficient of restitution. So when E is going to be equal to 0 for an perfectly inelastic collision, please write down, for perfectly inelastic collision, E is going to be equal to 0. Alright. So with this, the theory portion comes to an end and we have the numericals. But before stopping this one, I would like to go over certain things which it is already given here. In the test, you're going to get very short answer questions, which is given in page number 378. Very short answers to questions. Please learn this one. Just go over one by one. So friction is a non-conservative force. Why? So is work done in non-conservative force always negative? Comment. Learn the answers. Right? Similarly, go ahead to based on the energy and its conservation. So you got to just go on to see this answers which is here. Right? And also based on the short answer type questions here, you will find certain work is there, so please take down. All these things are quite important. In tomorrow's Zoom class, I will try to derive this one, number 3, I will try to derive this one. Maybe I can do that now itself. So it's quite important that I little more explain this one how it is. Let us read this one and try to explain how this one it happens, because these all things I'm going to consider it as a theory portion. On Monday's test, these all things will come, right? This all the questions. Two spring A and B are identical. They look similar. Both the springs are looking similar, but A is harder than B. Alright, identical springs, but one is very much hard and another one is small. That means Ka, what is K? Spring constant. Ka is greater than Kb. The B1 spring constant is less than A. On which spring more work will be done? So there are two springs is there. So one is hard and one is light. The A part is when they are stretched to the same distance. So first one is same distance is there, right? So let us write what is given here. Given is Ka is greater than Kb. The spring constant of A is much greater than the spring constant of B. Work done is going to be equal to half Kx square. That is spring constant. Work done is equal to half Kx square. So work done of A is going to be equal to half Ka x square. Work done of B is equal to half Kb x square. Now we are going to see the A part of this one. Look at this one. They are stretched through the same distance. That means XA is equal to XB, that is going to be equal to X itself. Distance is same. So one spring is here, another spring is there. This is A, this is B. This is also stretched in the same X distance. This is also stretched in the same distance of X. So we have put X as the same. Only A is different. Take the ratio of both of them. WA upon WB. When you take the ratio of both of them, half Ka x square upon half Kb x square. Half and half gets cancelled out. X square gets cancelled out. So you have Ka upon Kb is equal to Wa upon Wb. So keeping this into consideration, how do you find? Ka is already given as Ka is given as K is greater than Kb. This is bigger than this one. It's already given there. So what will happen? Wa, the work done in A will become equal to work done of B. So the answer is, which spring more work will be done? The spring of A, more work has to be done because of this particular thing. Now there is a second part of this one is also there. If they are stretched with the same force, only force is same. They are not saying about that distance. Force is same. Now when same force is given, how it will be, we need to find it out, right? So force is going to be equal to, we already know it is spring constant into distance, right? So what is distance is going to be equal to, we don't know what is the distance going to be equal to, but it is F upon K is going to be the value of this particular thing, which comes as X is going to be equal to F upon K. Now force is same, but this is going to be a different value. So since Ka is greater than Kb, it's already given there as Ka is greater than Kb. So what will happen here? If Ka is greater than Kb, so Xa will be less than Xb because it's inversely proportional. So Xa is going to be less than Xb. So following up here, work done is going to be equal to half K x square, and X is already equal to F upon this one. So half K F upon K the whole square, which is equal to half into k into f square upon k square, and this will get cancelled out. So it's going to be equal to half f upon k. So that's w. So w is going to be equal to half x into k. This is actually f square upon k. Now k is equal to f by x. How did we take this one from here? You have taken k is going to be f by x. You need not have k here, remove it and put f by x is going to be equal to half f square upon f by x. So what will be the value of w? W will become equal to half xf. That is the value of w. Based on this, we need to finally take the call on it. Which work done will be greater, which work done will be less. We already know xa is less than xb. So if xa is less than xb, what will be the work done? It's now directly proportional. So work done of A also will be less than work done of B, because we are giving the same force. At the same force, we have this value will be there. Now what are we trying to achieve in the whole of this one? We are trying to achieve a formula which will fit this question which is here. Work done is going to be equal to x into f divided by 2. What the question was? When it is stretched by the same force. When the same force is given and force is same, and that it is going ahead and stretching, x is the stretching for distance, and what is that happening? Work done is going to be there, right? It is going to have the work done. So which work done is going to be bigger and smaller? We have seen, since in the stretching part of it xa is less than xb, so work done of A will become less than work B. So that's the way in which we conclude. So please take down this one, it's a quite an important one. Let us go to another question here. Question number 4, which is here in this place. Look at this one. Force acting on a particle is given by, now this is a formula here. F is going to be equal to A plus Bx is a formula. Now find the work done in displacing it from, so the work done in displacing it from x is equal to x1 to x is going to be equal to x2. So what is work done? Work done is going to be equal to force into distance, right? So you have this as the value here. So F into dx you can call it as force into distance. Now this is the value, so you can write it as A plus Bx time of dx. That is the value of dw. W here. So dw is going to be equal to this much. You need to find out finally the value. So small work done is going to be equal to small distance here. But we need to integrate for the distance of from x is equal to x1 to x is equal to x2. So the total this work done dw is going to be equal to integration of x1 to x2 a plus bx into dx. So what is that value? It is going to be equal to x1 to x2 a dx plus x1 to x2 bx dx. These are all integration. We already studied this one. Now this is a into dx. This is here bx into dx. Integrate and see how it will become. So this will become a into x and x1 to x2 plus x dx. It will become b into x square upon 2. x1 to x2. Why is x square upon 2? X upon x power of 1 is there, no? So x square upon 2 will be there. And you need to put the value of x2 and x1 and then finally find out the answer. So that's what you find here. It is, once you do this one, x2 minus x1 will become, because when you put this one, it's going to be equal to a times of x2 minus x1 will be there for this particular thing, plus b times of 2, you can take it outside. Here it will become x2 square minus x1 square. So it is w. Okay, now the next one is 5th question. A body of mass m accelerates uniformly from rest. From rest position it is just accelerating. Okay, this body is accelerating. Yeah, we'll read it again. A body of mass m accelerates uniformly from rest to velocity v1. So the velocity is v1 is going to be the velocity here. It accelerates. From rest, u is going to be equal to 0, and under time 10 is t1. So what's the value here? So you'll find v1 is going to be equal to 0 plus acceleration into t1. So what is acceleration? v1 upon t1. So this is the equation number 1. Find the expression for the instantaneous power delivered to the body as the function of time. You can write down as at any instant of time t. At any instant of time t, what will be the velocity? Velocity v is going to be equal to 0 plus a into t. We know this one already. It is going to be v is going to be equal to a into t. It is an instantaneous velocity. Alright, it is instantaneous velocity. So if it is instantaneous velocity is there, what is a? Acceleration. We already know it was accelerating in this value. So put this value here. For instantaneous velocity, v is going to be equal to v1 upon t1 into t. So you get here v1 upon t1 into t is the instantaneous velocity you will find here. And the next one is, it is asking for instantaneous power. Instantaneous power. So power is going to be equal to force into velocity. We already know this one. So power is going to be equal to mass into acceleration into velocity. Forces and mass into acceleration. So you find two things over here. You find two things which is here. One is this velocity. Next one is the acceleration. This is coming from here. So doing here, what happens here? Acceleration you need to substitute, velocity you need to substitute. Acceleration is substituting from equation number 1. Bring it here. So power is going to be equal to m into v1 upon t1, and velocity is going to be equal to v1 upon t1 into t. This is from the velocity, instantaneous velocity, and this is from the acceleration here. So what will happen to the whole thing? M v1 square upon t1 square into t. That is power. So power is going to be equal to m times of v1 square upon t1 square into t. So that's a instantaneous power. You can also look at question number 6. Calculate the work done. So F vector is going to be equal to yi vector. It is along the x-axis here. I vector is x-axis. To move a particle, a position is given here from A to B. So you need to put the work done. Formula is there, and then force into distance, and you can do the integration of this one. So you will get the answer as an integration value. So you can see this, how it happens. So you will get this as a value of half joule is there, because dW is equal to 0 to 1 x dx is equal to x square by 2. So you get half joule. The B part of the question is dW is going to be equal to, when y is going to be x square is there, what will happen? So it's going to be 1 by 3 joules will be there. Right? So with this I close. So you got to read all of the questions and try to understand. If you don't know any of the question, please give me a message. We'll try to solve it. But remember, till this page number 382 until question number 23, you need to learn as the conceptual questions, very short answer questions, and the theory portion will be coming for the test. Thank you.